Hello, thank you, Guanta and Haifeng, for inviting me into this interesting session. So my presentation is about using data-driven models for urban stormwater studies. I'll be introducing 4 different cases for the application of data-driven models. So as we all know that if we do want to understand a system, it could be a urban catchment, or it could be a nature-based solutions for stormwater treatment. And we want to know what is the input and what is the output of these systems. And the best way is to do monitoring, of course. And we can collect data on the treatment alongside with the design and operation of the systems. And this is going to be the most reliable data that we have. And in the meantime, if we understand the physical processes, how the water goes through, how the pollution is being transformed or uptake, you can build up process models, which is relatively complicated, but it's possible and reflects the reality of the whole processes. And more recently, the data-driven models has been increasingly used to understand or to predict the system performance. And one benefit, of course, you don't have to understand the physical processes to construct those models, which can also have very good prediction ability. And in the meanwhile, if you can use the models in a good way, you can also inform some of the physical processes that is sometimes very complicated and hard to understand in real systems. So I'll be introducing 4 different application studies from stormwater quality modeling to the modeling of the treatment performance in stormwater biofilters, case 2 and 3, and also the urban waterways. And the data-driven approaches we've used covers different approaches. There's genetic programming, statistical models, and also different machine learning approaches. And the data we have monitoring data, which is great, and also good literature review data as well. So the first case is to model the stormwater quality in urban catchments. And we all know that the pollution generation in our urban catchments are highly complicated. There's sources of the pollution from human activities, and the pollution will accumulate in the pervious and impervious areas, which will be then flushed away upon the rainfall. And the whole process, especially the pollution accumulation processes, is subject to different climate conditions, catchment conditions. And in addition to that, there's also subsurface sources that goes into our urban drainage systems, like leakage or interflow leakage between the urban underground systems. So it's a very highly complicated process. And our aim was to try to improve the model performance, because the urban stormwater treatment models have been there for around 50 years, and they perform okay, but they are not to the extent that we were hoping for because of the complicated processes. And this purpose of this case was to try to understand what are the algorithms that can be used to represent the build-up processes, which is impacted by various climate variables. For example, Anderson dry weather periods, temperature, rainfall, or solar energy, etc. So how do we construct the algorithm or the model? We use the genetic programming, which firstly generate a list of populations. We call it initial populations, which is a list of different algorithms that is randomly generated. And then we check the fitness of the algorithms to our data. And if it's good fitness, then we can output the data. But often, the first round usually doesn't meet the fitness requirements. And then you can go copy, crossover, and mutation of those algorithms until it generates the next generation, and then goes back to fitness assessment. And with different multiple iterations, you can finally find out some algorithms that you are happy with with very high good fitness. And of course, we use different data from different urban catchments, both in Australia and also in US, including residential catchments, urban catchments, and also industrial catchments. So a very brief overview of some of the key results. We found out there's different algorithms that can be used for us to simulate this, to represent this build-up process. And we found the antecedent dry weather period, which is commonly used in the traditional build-up and wash-off models, is included as expected. But different from the traditional models, we also found that temperature actually is good for nitrogen and phosphorus when we want to predict, simulate the build-up process better. And we do find out that for different pollutants, you should be using different algorithms, as previously we only used typical algorithms that is applicable to all different pollutants. So this is a very simple case that demonstrates that how we can use those data-driven approaches to further improve the performance of those complicated nature processes. So this is case one. And case two is on modeling the stormwater biofilter performance. As we all know that stormwater biofilters or bioretention systems or rain gardens are very commonly used in nature-based solutions under the concept of sponge city. And this is a typical design of biofilter systems, where you have different layers and the water goes through different layers and absorbed by plants or uptake by plants. And they are physical-based processes to mimic the water flow through the systems, also to represent how the pollution is removed or retained in the systems. However, these are very complicated, and you do need a lot of good, high quality and high resolution data to prove that this model is working very well. And in the meantime, these systems are highly impacted by different design and operational variables. So the question was, why don't we just using data-driven approach and taking into the consideration of all those variables, and to see if we can give a good performance, and also if we can identify which are the key design and operational variables. So we constructed a model, so different type of models we call operational condition model or design characteristics model. Let me just briefly introduce what's the models. So we assume that outflow for model 2, we assume the outflow concentration is a linear function of all operational variables, which is ADWP, RI, flux, Cin, and the regression coefficients of these variables is a linear function of the design variables. So this is basically a multi-layer hierarchical statistical model. And the model 3 is the other way around. The outflow concentration is a linear function of design parameters, while the regression coefficient is a linear function of the operational parameters. And on top of that, we tried to exclude some of the variables to see if the model, there's better improvement in the model performance, or it's actually decrease of the model performance. And in that way, we can tell, okay, which parameters are important, which parameters are not. So again, some very overview of some of the results on nitrogen removal in stormwater biofilters. And we found out, okay, if we exclude vegetation or submerged zone, then your model performance will be much worse than the models with this vegetation type in submerged zone, which in a way reflects that these two variables are really important, and it is in good agreement with previous findings in the laboratory or in the field. And in terms of operational conditions, we found out the infiltration rate is also extremely important to make sure the model performs well, to make sure that you can predict the performance of the system by including this infiltration rate. And outflow concentrations is slightly less important, but it it does show an improvement if you can see the inflow concentration. So this is another case. We showed that how we can use data-driven models to predict the system performance while identify the key design operational variables. So the next case is also on stormwater biofilters. Instead of using statistical models, and we didn't come up with models, but instead using machine learning methods and then using data collected from literature on heavy metals. And then we use different feature selection functions of those machine learning methods to identify the key features. So the results from the model performance, as we can see, so we use the multilinear regression, neural networks, and a random forest. And we can see the model performance varied across different pollutants. The best was for CD, cadmium, the worst is for chromium. And also zinc was okay, but not that good in the validation stage. In terms of the differences between the models, they are not huge difference, but relatively random forest was the best. And then we use the feature selection methods using the regression coefficients or p-values from the multilinear regression, feature selection function, and also permutation importance function from random forest, and also another method called Bruta, which is also based on random forest. And we try to identify which are the top 3 most important variables from each of the methods. And as you can see here, ratio, infiltration rate, IR, and CIN are most selected as top 3 by those feature selection methods. And this is also in good agreement with previous studies on nutrients and phosphorus, but also previous studies on heavy metal performance in these systems. So again, this shows how we can use the machine learning models to achieve this purpose. And the last case I want to introduce is the application on the early prediction of campylobacteria in urban waterways. So basically, we collected a lot of samples from urban waterways in Melbourne, Australia. And then the second step was to inoculate the samples in different tubes in different volumes. So this is a standard microbiology methods. And they incubate at 42 degrees for 48 hours, basically 2 days. And then traditionally we use PCR to analyze the campylobacteria presence in these tubes. And you can see if there's 0 absence or 1 presence of campylobacteria in this tube. And instead of that, we also we took the samples, so incubated the samples, which we found very different coloring of the tubes after incubation. And so we thought, okay, maybe the color can represent something about the presence and the absence of the campylobacteria in those samples. So that's why we ended up doing spectrophotometer analysis. And then you can get absorbance at different wavelengths from 300 plus to 800 plus. And using the data we collected from spectrophotometer analysis, we can train our machine learning models, which can help us to predict the PCR presence, but also the probability of the PCR each sample. And using that, we can just compare the PCR observations against the PCR predictions by the machine learning model to see if the models work well. And also you can use probability to estimate the presence of campylobacteria to predict or estimate the most probability number in the very raw stormwater sample, raw urban waterway samples. We use 3 very common machine learning methods: logistic regression, supported vector machine, and a random forest. And 3 major scenarios tested, but I'll be presenting 2 results of 2 scenarios, which we used the controls for training and the samples for testing. The The controls means the positive and negative